Hello everyone, my name is Makumba Gerard of EduMath. In this video, we are going to see how to derive a formula based on Newton-Raphson's method for solving the roots of simple functions, drawing the flowchart, and performing a dry run to find the root to such functions. But hey, before we continue, if you are new here at EduMath, consider subscribing and hitting the notification bell such that you can be notified of the new videos that we make and upload every day. So let us get started and see you there. So I have an example. So our example is right here, part A. Show that the formula based on Newton-Raphson's method for finding the root is this. This can be derived quite easily. We are going to do it, but I'm going to link the cards, alright, about the Newton-Raphson's method. So when the card comes, feel free to click on it and you learn more about Newton-Raphson's method. For the moment, let's get started showing. So we'll let fx to be equal to 0 such that fx is equal to this function, because this function is also equal to 0, to x power 3 plus 5x minus 8. Then from here we can be able, because Newton-Raphson's formula is xn plus 1 being equal to xn minus fxn divided by f derivative of xn. So from here, we can discretize this function. This is a continuous function. We discretize it to have fxn giving us 2xn power 3 plus 5xn minus 8. Here we have discretized it. We need to come up with f derivative xn. Now we have to differentiate this, which is a continuous function. So we shall have f derivative of x giving us 6x power 2 plus 5. Discretize this, we shall have f derivative of xn being equal to 6xn power 2 plus 5. So we have everything required to substitute in the formula right there. So xn plus 1 is going to be equal to xn minus fxn is right here, 2xn power 3 plus 5xn minus 8, everything divided by 6xn squared plus 5. Next step, we get the LCM. LCM is 6xn squared plus 5. This will now become 6xn times xn. You get 6xn power 3. xn times 5, you will get plus 5xn minus, this will be 2xn power 3 minus, this negative is entering, 5xn plus 8. So we collect their like terms. We shall have 4xn power 3, this and that vanishing, and plus 8 divided by 6xn power 2 plus 5. So this here is xn plus 1. Let's check on what was required of us. Yep, it is exactly that here. Yes, so where small n is equal to 0, 1, 2, 3, and they continue. So we are done showing that based on Newton-Raphson's method, this equation can be solved by this formula. Now part B, we are going to draw a flowchart that reads the initial value alpha of the root. So we are going to have the initial value alpha of the root, right? Okay. Computes and prints the root of the equation when the error is less than 0.001, right? Then after, we shall have to dry run, to perform a dry run, but with the initial approximation, which is alpha being 1.1, and our answer should be to 3 decimal places. Now here, the error has already been given. There is no need of using this information of 3 decimal places to get the maximum possible error. We are going to use this as our error in the decision box. So let us get started. Part B, alpha is our initial approximation. Then we have the error as being equal to 0.001. This here. So every flowchart starts with a start button. The next step is we are going to assign smaller n. You see from here, smaller n, that's the very first step. So this is our assignment box. Smaller n is going to start with 0. Having assigned the n to be equal to 0, the question is now telling us to read the initial approximation of alpha. So reading is a command. So within this command box, we are going to read our initial approximation alpha, right? So having read alpha, which is the initial approximation, we have smaller n, we have assigned it, so we can be able to substitute in this, meaning we are now going to bring in the arithmetic stage or arithmetic box here. So this is where we shall have to compute xn plus 1 being equal to this 4xn power 3 plus 8 all over 6xn power 2 plus 5. So after computing xn, remember we have alpha, which is our initial approximation. We shall be required to compute the error. So that is the next step, and the error is what helps us to determine whether to continue or not. So we are going to bring in the decision box. So here is our decision box, which is always having a control statement in the form of a question. So we have to ask, is xn plus 1 minus xn less than or equal to? The error was given to us, which is now 0.001 in the form of a question. So if no, we are going to take this root here. This is if no, and smaller n is going to be assigned. We are going to take another iteration, and smaller n is going to go to the next value. So here, this is when the computed error is less than the standard error. So n is going to go to another value. So n will become n plus 1, going to another value. Consequently, even the values of x will go to another value. So we shall have the values of x, which is xn, becoming xn plus 1. Right, and then we shall join the flowchart at this point here. How about if we compute the error and we find it less than the standard given error there? What shall we do? Let us see what the question tells us. The flowchart reads the initial value alpha of the root. We have seen this. Then this flowchart computes and prints the root of the equation. So it computes the root. We have seen how we can compute the root here. We compute the root from here. Then we check on the error, because we base on the error to decide whether to continue or not. So here we ask ourselves, is the computed error less than the standard given error? If the answer is yes, then we shall go back here and we print. So that means we are going to print the root of the equation. Now print is a command, and therefore we are going to use a box which is like this, a parallelogram. So we shall print xn plus 1, and after printing xn plus 1, we shall stop. And the stop button is always in the oval shape, so we are going to bring it in. So we stop. So this here is our flow chart, and we have to use this to perform a dry run. And now part C, taking alpha. Alpha is the initial approximation as 1.1 we need to perform a dry run for the flowchart, and then we have to give our answer to 3 decimal places. Let's get started. So our dry run is going to be done within this space here. I'm going to assign n first. N will lead us to xn. Then xn will lead us to computing xn plus 1. Xn plus 1 will lead us to computing the error, which is the magnitude of xn plus 1 minus xn. And then we shall make a decision of whether to go this side or this side. So from the decision box or decision stage, after satisfying the condition for the control statement, we take the alternative part. So let's get started. Let me draw my table here. So we are going to start by assigning n to be equal to 0, smaller n. So when smaller n is 0 here, alright, we shall have to get x naught. X naught is the initial approximation, and it is the same as alpha, right? So we shall have to read the value of alpha, and from the question, alpha is equal to 1.1. So that is what we have to read. Alpha is 1.1. So our initial value alpha is equal to x naught, which is equal to 1.1. So we read it and we put it here, 1.1. So we have read alpha. Get ready with our calculator there. So we are going to compute the beta approximation xn plus 1, right? That's what you are going to compute next. So when you put in 1.1, you are going to get 1.6000, 4 decimal places. So we have finished computing here. We are moving down. We need to compute the magnitude of xn plus 1 minus xn, right? In other words, we need to compute the error, and then we compare it to the standard maximum error given to us. So let's get 1.6 minus 1.1. We are getting 0.500 for dps. So is this value 0.5 less than 0.001? No, this value is bigger than 0.001. So that means smaller n goes to another value. So we shall add a 1 on this previous n, and n becomes 1 here. Then xn becomes this value here. So xn takes on the values of xn plus 1, which is now 1.6000. And then we come and we substitute here for xn. Let's substitute in our calculators and see what we get. So when we substitute in our calculator, we are getting 1.1976. Then we need to take the error. We are moving down. We need to get xn plus 1 minus xn, this minus that, which is 0.4024. So is this value less than 0.001? No. So that means the n goes to another value. So we are going to add a 1 on this previous n here to make it 2. This xn now becomes xn plus 1, or xn takes on this value here, which is 1.1976, right? Next, we need again to substitute xn, which is this, in the formula here to get xn plus 1. So let's get ready with our calculators. So when you compute xn plus 1 becomes 1.0930. We are now moving. We are done with computing this. We need to get xn plus 1 minus xn, which is our error. So let's do that. So this here gives us 0.1046. Is this value less than 0.001? No. So smaller n takes on another value. We add a 1 on this to make it 3, and then the value xn takes on the previous value of xn plus 1. So this comes here. I have 1.0930. So we feed them here where there is xn, feed in 1.0930. On our calculator, we shall have to get 1.0867. So having computed this, we move down. We need to get the error here. That is xn plus 1 minus xn. So this value minus this value, we are getting 0.0063 in magnitude. So is 0.0063 less than 0.001? No. So we take this root again. So smaller n is going to take on to be added by 1 to make a 4 here. And then the value of xn is going to take on this, which is 1.0867. Again and again on our computer here, a calculator, we have to compute for xn plus 1, this using this formula here. So we are getting 1.0867. You can see this here is the same value. What does it mean? This minus that, the error is going to be 0.0000. So is 0.0000 less than 0.0001? Yes. So what do? We are going to print xn plus 1, which is equal to, xn plus 1 is now equal to 1.0867. Then what happens next? We stop. That means there is no more work to be done here. But let's check on what the question required of us. The question required we to find the root of the equation this. So now we are going to make a conclusion about the root of the equation. So the root of the equation, 2x power 3 plus 5x minus 8 equal to 0 is, we go to our printout and we write this to 3 decimal places, is 1.08. Round this to 3 decimal places, this will be 73 dps. So let's head for our trial question. So our tryout question is right here. Part A, they need us to show that the equation has a real root between 3 and 4. We shall use sign change here. Show that the Newton-Raphson's formula for approximating the equation of the root of this is this. I'm going to link in the cards the videos about Newton-Raphson method. Then we draw the flow chart which prints the root of the equation within the error of 0.05. Yes, you have to interpret this correctly. 0.05. Then carry out a dry run of the flow chart and obtain the root. So once we do that successfully, just know we shall be moving together as mathematicians. Once again, if you are new here at EduMath, consider subscribing, consider recommending the channel to your friends such that we can move as mathematicians. So I want to thank you very much for being part of my audience and God bless you.